Hello, in this video we will talk about type of natural numbers. Natural numbers are numbers that we use for counting 0, 1, 2, 3 and so on. So how would we define type of natural numbers in Haskell? We would write data type not equals and two value constructors 0 and successor of n, that is next natural number after this natural number. This code in Haskell can be translated to Scala in the following way. We can define trait not with two children, case object 0 and case class successor of n, and this code can be translated to Java as we can define interface not with two children, class 0 and class successor of n. Well, surely there are some differences between these code fragments in Haskell, Scala and Java. For example, in Scala 0 and successor of n will be types themselves, while in Haskell 0 and successor of n won't be, but we will ignore such small differences now. Okay, so how will type of natural numbers be defined in type theory? As always, we can formulate several rules. First rule is a formation rule. It states that in every context gamma, not is a type. Next rule, constructing rule, formulates how to construct values of this type. In every context gamma, 0 is a value of type not, and if in a context gamma n is a natural number, then successor of n is a natural number. Next rule is eliminating rule, which is used for pattern matching. If C1 is element of type C and C2 is an element depending on natural number n and having type C, then we can match on natural number x, whether it is 0 or successor of n. So if x is 0, we have C1. If x is successor of n, we have C2 of n. Next rule, computation rule, or so-called beta reduction. It describes what happens if we apply constructors firstly and then eliminator. So obviously if we have 0, we have first argument. If we have a successor of n prime, then we have second element with n prime substituted instead of n. And there is no necessity in uniqueness principle for type of natural numbers. Okay, let's look at some code. We use library proving ground, define not as a type, it will be printed not. We define this type as an inductive type with constructor 0 and constructor suck, which takes a natural number and returns a natural number. And this is definition of our type as an inductive type. Well, we can see now that it's really inductive definition. So in order to define next natural number, we need to have previous natural number. Here is an induction. We will denote 0 as 0, suck as suck. We define two variables of this type and several constants. Okay, so let's define function of doubling a natural number, that is multiplication by 2. This is a function that takes one natural number and returns a natural number, and we will make a pattern matching on its argument. So, if an argument of function double is 0, then 2 times 0 is 0. And we need also to describe what will be result of our function if we apply it to successor of n. And m here is a result of our function after application to n. So we know that 2 times n is m, and we need to calculate 2 times n plus 1. Well, it's obviously 2 times n plus 2, so we should return m plus 2, that is successor of m. Let's check that our definition works. We feed this code to REPL. I've already started REPL with command sbt-mantle test console. Okay, let's check. Double 1. Maybe it's 2. Let's print in fancy way. Yes, it's 2. Double 2 is 4. Double 3 is 6, and so on. Okay, so let's define a function of addition of natural numbers. This is a binary operation. It takes two natural numbers and return a natural number. And we will make pattern matching on its first argument, whether it's 0 or successor of n. Well, if first argument of addition is 0, then we return this lambda, just which maps m to m. It should work because 0 plus m is m. So we maps if first argument is 0, then we maps second argument of addition to itself. And then we need to describe our function if we apply it to successor of n. Add n is a value. Add n is our function addition being applied to n as its first argument. So what should we do? We have function n plus something and need to define function n plus 1 plus something. Well, naturally it will be add n m and successor of it. Let's check. Okay, let's check. add 1 and 2. Okay, let's make it fancy. It's 3, for example. 2 plus 3 is 5. Okay, it works. Okay, it's all. Thank you for watching. See you in the next video, and now you're ready to solve some problems with natural numbers. For example, implementing tripling of natural number, finding predecessor of natural number, finding square of natural number, and so on. See you!